Hey guys, welcome back to Genius Learning. So in this video, I want to show how we use the law of cosines in electromagnetism, and specifically for this example, image charges, which is a method in electromagnetism to calculate the charge of a particle at a distance. And so let's label this sphere here Q, which represents the charge that it has. And just to be clear, this is a sphere in 3D, and so let's put some of these lines on it and make it pop. Okay, so we got a sphere, and this sphere has charge Q all over it. Okay, and then our goal is to calculate the charge or the electric field that this particle here, so we'll say that at this point, right, there's another charge, or we just want to measure the electric field at this point due to the charge coming from this sphere. Okay, so the way we do that is first let's work with the sphere. And in the previous videos I already showed how all of these vectors and all the position vectors in here, the position coordinates in here are derived. So I'm going to kind of go quickly through this part. So we have our radius, which we're going to label big R, and this is a differential area right on the sphere, right on the edge of the sphere. And so differential area right on the surface of the sphere, and this big R represents the size of the sphere. So the size of the sphere is not going to change, and so that's why we write big R. Okay, and so we also know that theta comes down from the Z. Okay, this component here is going to be R sine theta because it's opposite over hypotenuse, and this side here is going to be R cosine theta. Right, so we're just going to label this side here R cosine theta, R sine theta. Okay, perfect. And let's project this down onto the XY plane. Right, this arc right here is the same thing as this arc right here, and we're going to project this R sine theta down here, and this one is the same thing. Okay, so R sine theta was projected down from here onto here, and we know that in the XY plane, phi goes from X towards Y all the way around, and a small change in phi is d phi. Okay, leaving us with the arc length here of R sine theta d phi. Okay, R sine theta is the radius, and then d phi is the angle. So this angle right here is the same as this one. All right, and so we did this part already. Okay, so now let's do the part where we can use law of cosines for electromagnetism. So we want to calculate the electric field at this point away from this sphere that has this charge on it. Okay, so what we're going to do is we're going to connect a line from dA, our differential area, all the way through into this direction. So let's do something like this. Oof. All right, got it. Okay, so this is a vector line. So what we're doing is showing that the electric field from the surface of this sphere is projected in this direction as a vector. Okay, and it's passing through that point. And in an electromagnetism problem, really you would have a vector here, you would have a vector here, a vector here, and basically all along the top of this sphere pointing towards the point. And you'll later learn that the vectors that are exactly opposite to each other, which are this one and this one, are going to cancel out. And so all the vectors actually cancel out except for the ones that are pointing exactly in the z direction. Okay, so, but that's for a later video. And so for now, we're just going to point this vector here, and we'll call it the electric field vector, you know, differential of the electric field. That's not too important, but just for labeling. Okay, so now we also have to identify that from the bottom, from 0 right here, all the way to this point, this whole entire thing here is z. Okay, so this entire thing from the ground, from 0, from the center of the sphere all the way to the point is z. And now, since we have our cosine in the way, we need to label this point right here. So we need to identify this region right here. Okay, we're going to label that z, the entire length of this, minus this r cosine here. Okay, so you see how I'll take the entire length minus this, which is just going to leave me this piece here. And so z minus r cosine is that area right there. Okay, so now that we have this side and we have this side of the triangle, we need this vector. This vector here, as soon as it was projected this way up to the point, is r. All right, so we have a big triangle up here. So I'm just gonna kind of highlight it so we can see it clearly. So this entire triangle up here is what we're gonna work with now. All right, and so for this triangle, we need a new angle that's gonna represent this part, because it's not the same as this or phi down here, so it needs its own angle. We'll just call it this angle here. Okay, so this angle here is the same thing as this angle here. All right, complementary angles. And that's just important for later, for a different type of problem, but just to show how everything connects. So now we have everything that we need here. And I just want to be clear on what we're looking at. We have this top triangle up here, which is r, and this side is z minus r cosine theta, and this bottom part is r sine theta, and this is the angle. Okay, this triangle is the one in pink right here. All right, and then we also have this smaller triangle here, which is theta. This side is r sine theta, this side is r cosine theta, and this is r. Okay, so these are the two triangles that we're working with. All right, so now let's use Pythagorean theorem. Okay, so we want to know the value of r. All right, and the reason we want to know the value in r is because in electromagnetism, the formulas that we use requires the radius from the charge to the point of interest. Okay, so we need the value of this r. So to get the value of r, let's use Pythagorean. Okay, Pythagorean is c squared is equal to a squared plus b squared. Okay, and let's use it for this top triangle right here. So this one up here. So we're gonna do r squared is equal to a squared. So we'll label this side A. So we have this triangle here, which is C. We'll label this A and we'll label this B. Okay, so this one is the same thing as that. And so now we're gonna do C squared, okay, A squared, which is gonna be Z minus R cosine theta squared plus B squared. So B is R sine, and so that's gonna be R sine theta squared. Okay, so let's FOIL it out and see what we get. We're gonna have R squared, and for this we're gonna have Z squared minus 2Z R cosine theta plus R squared cosine squared theta. Okay, now we're done with that. And here we have plus R squared sine squared theta. Okay, so let's combine things. These two things right here we can combine. So we know that cosine squared theta plus sine squared theta is equal to 1. Right, we can pull out the r squared. And so this value in here is equal to 1. And so now we get r squared is gonna equal, I'll move this big R squared to the front just for preference, plus Z squared, it could be any of these two, and then minus 2ZR cosine theta, and last I'm gonna put the square root over everything, and so we have R squared plus Z squared minus 2ZR cosine theta. Okay, so this is the radius from here, from the charge of the sphere to the point, and this up here is the law of cosine, right? Which is the same thing as the bottom one, except we put the 2 as a square root on the other side. Okay, so they're the same thing, but we found the law of cosine in just using our triangles here. All right, and then the last thing that you're gonna need is you're gonna need cosine, okay, of this angle here. So the cosine of that angle is gonna be Z minus R cosine theta, which is the adjacent over the hypotenuse, which is R. All right. So the reason you're going to need that is because up here, when you have your electric field pointing from the surface of the sphere to that point of interest, you want to calculate this vector and this vector and all the other ones. And so this one here could be found by doing another triangle up here later on, and you'll find that this angle and cosine of this angle is very important. So that's for another problem, but just know that we would need this, which is the law of cosine, and this angle here. And so just for a small proof of law of cosine, let's take this example here. We have these two triangles. Okay, we have these two triangles, which is similar to what we have here. We have this pink triangle and we have this smaller one. Okay, and so A is this entire side right here. Okay, C is this entire side. B is this side here. Okay, so you can look at this and relate it to here, but all I want to do is just prove the law of cosine and how it was found differently using this method up here. Okay, so here we have this height, and the angles in here is going to be capital A, capital C, and capital B. They represent the angles in those spots. All right, and then lastly, we have this value is going to be x from here to here. And so then that means that this spot here is going to be the entire length of A minus x. And so we have A minus x here. The same way that we did with the z and the r, we did the entire length of z minus r cosine, and it left us with z minus r cosine here. Okay, so that's that part right there. All right, so now that we have all that, let's we're going to use Pythagorean for this situation also. And so we're going to do b squared is equal to, we're going to do the triangle, we're going to do the Pythagorean for this triangle right here. Right, so let me highlight that so there's no confusion. So this yellow triangle right here is what we're going to be working with right here. So we got b squared, which is the hypotenuse, is equal to h squared, and this bottom here squared, a minus x squared. So all the sides of the triangle squared, and then the hypotenuse squared. And so now if we FOIL that out, we're gonna get a squared minus 2ax plus x squared. Right, so let's put the x squared over here. So we got h squared plus x squared, right, plus a squared minus 2ax. So I didn't change anything, I just rearranged it. And I rearranged it so that way we can identify that h squared plus x squared is h squared, which is this, x squared, which is this, and that's going to equal c squared. So it's its own Pythagorean in here. So c squared is equal to h squared plus x squared. So this could be changed to c squared. And so that's going to equal b squared. Everything comes back down, right? And so we have one last move to make, and that's this x right here. All right, so let's look at this angle right here, because this is the angle we want to work with in order to identify what this x is. So let's do the cosine of that angle, b. That's going to be adjacent over hypotenuse, right? And so we pass the c over, we're going to get c cosine of b equal to x, which is perfect. That's what we want right here. So I'm going to write it out, c and then cosine of b, right? And then we bring down everything else. We got a, 2, I'm just gonna write it backwards. All right, a squared plus c squared equal to b squared. All right, so then if you notice, this is the law of cosine. Okay, so you can write a squared, and then you'd have to rearrange these. You could write c squared, you'd have to do the same, and b squared. So all three of them, depending on what angle or what side you're trying to find. In this particular case, we found b squared. And so this is the law of cosine formula. And this is how we derived it for our electromagnetism problem. So you can see the similarities. Okay, let's just separate this. And this is separate also. Okay? All right.